Alright, so net ionic equation will be Ca, let me see, is everything balanced? Okay, Ca2 plus 2Cl minus plus 2Na plus CO3 2 minus gives me 2Na plus 2Cl minus plus calcium carbonate solid. I'm sorry for Bobo. Alright, I'm going to eliminate my spectators. Sodium. I'm going to end up with Ca2 plus carbonate 2 minus gives me calcium carbonate solid. Alright. The following, okay, so in this one we want to identify which of the acids here is going to be the strongest. Okay? And strongest acid is going to be the one that comes apart the most, that dissociates the most. And it's pretty obvious that that is going to be this one here because everything is dissociated. And the one that's the weakest will be the one that has the fewest molecules separated into ions. So it looks like that is going to be, I just have 2 positives, 2 negatives, 3 positives, 3 negatives. So this is going to be the strongest, and this will be the weakest, and then of course this will be in between. Okay, we want to classify each of the following dissolved substances as strong electrolyte, weak electrolyte, or non-electrolyte. Okay, so let's first identify the non-electrolyte. So if it's molecular and it's not an acid, it is going to be a non-electrolyte. Okay? If it's an ionic compound, it will be a strong electrolyte. Alright, we have an acid here. Is it on our list of strong acids? If it is, it's going to be a strong electrolyte. Alright, here we have another acid. It is not on our list of strong acids, so this will be a weak electrolyte. Here we have a base, potassium hydroxide. It's on our list of strong bases, so it will be a strong electrolyte. Okay, you can try that one on your own. Alright, we want to write a balanced molecular equation for the reaction between aqueous solutions of acetic acid and barium hydroxide, and write the net ionic. Okay, so I have plus barium hydroxide, balanced molecular equation, so it's going to have the hydrogen hooking up with the hydroxide, so I'm going to end up needing 2 of these. So I'm going to end up with 2 waters plus barium with the acetate. I'll write the same way they wrote this. The H has come off, right? It went with the water. And the acetate ion is the -1, so I'm going to need 2 of those. Okay, so that's the complete molecular. So this is barium acetate. So acetates are always soluble, right? This is a liquid. This is the driving force that makes the reaction happen. Okay, so the net ionic, this I'm not going to show ionized because it's a weak acid. But I will show, so I'm going to show this as all by itself, as a molecular substance. I am going to show barium ionized. The water, I'm not showing ionized because it's a molecular compound. It's not there as ions. And the barium acetate I will show as ions. It's a strong electrolyte. Whoops. Plus 2. Okay. So net ionic, the only thing I can eliminate here is my barium. So what I have left is CH3COOH plus 2OH gives me 2 waters plus 2 Okay. Okay, we want to write a balanced molecular equation for the reaction of carbonic acid and potassium hydroxide, and then write the net ionic. Okay, so we have carbonic acid, H2CO3, plus potassium hydroxide, and complete molecular is going to have the potassium, I need 2 of those because carbonate's a -2 ion, plus water, and I'm going to need, let me see, I'm going to need 2 Ks, so I'm going to end up with 2 waters. Okay, so let's see about writing the complete ionic. So the potassium carbonate will be aqueous, it will be soluble, right? Water is going to be a liquid, it's not going to be ionized. So carbonic acid is a weak acid, so I am not going to show that ionized. Okay, but this ionic compound, potassium hydroxide, is going to be ionized. So I'm going to have 2K plus 2OH minus. And I'm going to form 2K plus CO3 2 minus plus water, plus 2 waters. Okay? So the only thing I can eliminate here are my 2 Ks. Okay? So I'm going to end up with H2CO3 plus 2 hydroxides are going to give me CO3 2 minus plus 2 waters. Okay. Alright, we want to look at the reaction between aluminum and hydrobromic acid. And if we remember, the hydrobromic acid is strong. The aluminum will displace the hydrogen, so I'm going to end up with aluminum bromide and hydrogen gas. That's my driving force. I got a gas out of here. Aluminum bromide is going to be soluble. That's going to be aqueous. So I'm going to end up with my aluminum here is a solid, right? So I got to. It's not an ion. It's not an ion. Aluminum plus. I'm going to ionize this. I'm going to end up with an H plus a Br minus, and I'm going to get out of that an Al. Whoops, I didn't balance this. I need 3 bromine here, but if I do that, I'm going to actually need 6 here, right? So I'm going to need 2 of those, and I'm going to end up with 3 hydrogens, okay? So I need 2 aluminums, 6 of those, 6 of those. I'm going to put 2 aluminum plus 3s, or 3 pluses, plus 6 bromine 1 minus, whoops, it's a minus, right, plus 3 H2s. This is a gas, remember? Okay, so aluminum on this side and aluminum on this side do not cancel each other out, because this is a metal, right, piece of aluminum, like aluminum foil, and this is an ion. This is part of an ionic compound. They do not cancel out. Really important. Just like my hydrogen ions do not cancel out with my hydrogen gas over here. So the only thing that cancels are my bromine ions, and I end up with 2 aluminum zeros plus 6 H pluses gives me 2 aluminum 3 pluses plus 3 hydrogen gases. Okay. Alright, write the balancing molecular and net ionic equation for the reaction between magnesium and cobalt sulfate. Okay, so one of the things we need to do is decide whether or not magnesium, so here's the equation, right? We have magnesium and cobalt 2 sulfate. Okay, so I need to look at if I use standard reduction potentials that are on the sheet that you have, I want to identify, I've got magnesium here, and it's got to be strong enough to replace cobalt +2, so that would be right here. Now let me orient myself in this table. I do know group 1 metals are going to be the strongest, so this must be the strongest side of the table, and this is weaker. So what this suggests, if strong is down here and weaker is up here, that in fact magnesium is stronger than cobalt. So this will happen, okay? So when this happens, I am going to end up with magnesium sulfate and cobalt, okay? So if I write the net ionic equations for this, let me do that. I'm going to end up with cobalt 2+ plus sulfate 2-, giving me magnesium 2+, and plus I have a magnesium here all by itself, right? Plus sulfate 2- plus metallic or solid cobalt. Okay? So the magnesium does not cancel because one's an ion and one's a metal, solid, right? Same thing with the cobalt. The only thing I can eliminate as a spectator is the sulfate ion. So I really have magnesium and cobalt involved in the reaction, and so this is cobalt's a 0, magnesium's a 0, right? So it wants to know which is oxidized and which is reduced. Leo says Gur. Or I can look at which one of these has a charge that's been reduced. So magnesium's charge went from 0 to +2. That's an increase in charge. Cobalt has a 2+ going to a 0. That's a reduction in charge. So cobalt is reduced and magnesium goes the other way, so it must be oxidized. Alright, similar question. Will an aqueous solution of iron 2 chloride oxidize magnesium metal? Okay, so we need to know, is this magnesium stronger than the iron so that it will displace it? So magnesium again is down here. Iron 2 is way, whoops, that's fluorine. Iron is way up here. So this is the strong side. So magnesium is certainly strong enough. So I'm going to end up with magnesium chloride and iron metal. Alright, so that's the molecular formula. My net ionic is going to be Fe, let me see, is everything balanced? Yep. Fe2+ plus 2Cl- plus magnesium metal, right? I'll put that as a solid. Gives me, whoops, gives me magnesium 2+ plus 2 chlorine plus iron solid, right? So when I look at this, iron and iron do not cancel because one's an ion, one's the solid. Same thing with the magnesium, one's the solid metal and one's the ion. So the only thing that I can eliminate is the chlorine. So I'm going to end up with Fe2+ plus magnesium, which is a 0, becoming magnesium +2 plus iron 0. And in this case, the metal that has been reduced is the iron. It goes from 2+ to 0. That's a reduction in charge. This is reduced, which means this has got to be oxidized. Alright, which of the following metals will be oxidized by lead nitrate? So this is a lead. This lead must be a +2, so that's right here. Lead 2. So let's identify the others. We have zinc, we have copper, and I'm just going to assume it's copper +2, and iron, and there's iron, right? So the only one of these that is stronger than this lead is the zinc. So the only one that will be involved in that reaction is the zinc. All the others would be a no reaction. Okay. Alright, we're on 411. So we want to calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. Okay, so molarity is moles over liters, right? I have 23.4 grams of sodium sulfate, and let me see, 1 mole of that is I'm sure you can calculate this yourself, but it's 142.0 grams, right? So it's 20, turn on my calculator, clear that out. 23.4 divided by 142 grams gives me 0.164 moles, and I'm going to divide that by liters, and 125 milliliters is 0.125 liters, so I'm going to take that number I got and divide it by 0.125, and I get a molarity of 1.31. I think I have a decimal point in the wrong spot, maybe? No? Alright, and looks like I should have 3 sig figs, so it's 1.31. Okay. Take a look at the next one. Calculate the molarity of a solution made by dissolving 5 grams of glucose in sufficient water to form exactly 100 milliliters of solution. So again, big M is moles over liters. I have 5.00 grams, I'm just going to say, of sugar, and 1 mole of sugar. If you get the molar mass, I got 180.18 grams. This is going to give me 0.002775 moles. I'm going to divide it by 0.1 liter, and that's going to be 0.0278. Now, you could look at this and say this is 1 sig fig, but they said here exactly 100, which means you're going to treat it like a counting number. So this is 3 sig figs, so I'm going to make that 3 sig figs as well. 0.0278 molar. Okay. What are the molar concentrations of each ion present in a 0.025 molar aqueous solution of calcium nitrate? So if I have calcium nitrate, calcium's a +2, nitrate's a -1, so I need 2 of those, right? So for every 1 mole of this, I'm going to get 1 mole of calcium and 2 moles of nitrate, right? So the volume's not going to change, so if I have 0.025 moles of this, I'm going to have 0.025 molar of this, and I'm going to have twice as much, right? I'm going to have 2 moles for every one, so I'm going to have 0.050 molar of the nitrate ion. Alright, so what is the molar concentration of potassium ions and 0.015 molar potassium carbonate? Same kind of thing. I have potassium, KCO3. I need 2 of those because carbonate's a -2. So if this is a 0.015 molar, for every one of these I'm going to have 2 K pluses, so it's going to be double that, or 0.030 molar. Alright, how many grams of sodium sulfate are required to make 0.35 liters of 0.5 molar sodium sulfate? So there's a couple ways, different ways you could do this, but I'm going to start with my 0.350 liters of sodium sulfate. Okay? What I know based on the molarity, because it's 0.5 molar, is that in 1 liter there are 0.500 moles of sodium sulfate, right? And in 1 mole of sodium sulfate there are going to be 142 grams. So if I multiply this out, I'm going to get 24.9 grams. 3 sig figs, right? Alright, how many grams of sodium sulfate are in 15 milliliters of 0.5 molar? So I got 15 milliliters here of sodium sulfate, and what I know is because it's 0.5 molar, that's 0.5 moles per liter. A liter is 1,000 milliliters, it has 0.50 moles, right? So that is going to be 1.06. So we're going to make it, 2 sig figs, because that's what we have here. It's going to be 1.1 grams. Second question is how many milliliters of this are needed to provide that many moles of salt. Okay. So 0.038 moles of the salt, and salt is sodium sulfate. You do know that salt means ionic compound, doesn't mean necessarily table salt, right? And what I know based on the molarity is 0.50 moles is 1 liter, or because they want it in milliliters, I'm going to say 1,000 milliliters. So this is going to come out to be 0.038 times 1,000 divided by 0.5 is going to give you 76 milliliters. 2 sig figs, right? Alright, so how many grams of sodium hydroxide are needed to neutralize 20 milliliters of 0.15 molar sulfuric acid? Okay, so I can either use MAVA equals MBVB, adjusting for the number of hydrogens and hydroxides, or I can use stoic, right? Alright, so let's use stoic on this one, and you can do it whichever way works for you. So I got 20 milliliters of sulfuric acid, and what I know based on this molarity is for 1,000 milliliters I have a 0.15 moles of H2SO4, and I need the balance equation up here. So H2SO4 plus sodium hydroxide are going to give me sodium sulfate and water. So I'm going to need 2 of these, and I get 2 of these, right? So for every, based on that, for every 1 mole of this, of H2SO4, I need 2 moles of sodium hydroxide, right? And I want to know grams of sodium hydroxide. So for every 1 mole of sodium hydroxide, I have 40.0 grams of sodium hydroxide. That's its molar mass. So this is going to give me 0.24, let's see, 3 sig figs, 0.240 grams of sodium hydroxide. Okay. One commercial method used to peel potatoes is to soak them in a solution of sodium hydroxide for a short time. Sounds like a real chemist solution. Remove them from sodium hydroxide and spray off the peel. The concentration of sodium hydroxide is normally between 3 and 6 molar. Sodium hydroxide is analyzed periodically. In one such analysis, 45.7 milliliters of sodium hydroxide is required to neutralize 20 milliliters. Okay, So for this one, let's use MAVA equals MBVB, okay? So let's write the balance equation first. H2SO4 plus sodium hydroxide gives me sodium sulfate plus I'm going to need 2 waters, and I'll need 2 of this, right? So MAVA, so my molarity of my acid times the volume of my acid times the number of H pluses, right, is going to equal my molarity of my base times the volume of my base times the number of hydroxides in the formula. Okay, so my molarity of my acid, I got 0.5. Volume, I can use milliliters here as long as I use milliliters on both sides. Number of hydrogens in this formula is 2. Okay, molarity of my base is what I'm trying to figure out. My volume of my base, here I am using milliliters, so I can use milliliters on both sides, 20 milliliters, times the number of hydroxides in this formula, and there's only 1 hydroxide, okay? So if I want to solve for my molarity of my base, I'm going to divide both sides by 20 milliliters, and I get 2.29, and this is going to be molar. 3 sig figs? Yep. Okay, so a sample of 70.5 grams of potassium phosphate is added to 15 milliliters of silver nitrate, resulting in the formation of a precipitate. Write the molecular equation. What's the limiting reactant? Calculate percent yield, the theoretical yield in grams of that precipitate. Whew, this is a big one. Alright, so let's write the balanced equation. So I have potassium phosphate. Phosphate's a -3, so I need 3 potassiums plus silver nitrate, and I get a precipitate. So I'm going to end up with potassium nitrate. That definitely won't be the precipitate because both of these would always be soluble. But I am going to end up with silver phosphate. Okay, and that is going to be my solid. So let me see, I need 3 of these, so I need 3 of these. Okay. So what's the limiting reactant? So what I'm told is I have 70.5 milligrams of this, right, potassium phosphate, and I have 15.0 milliliters of 0.50 molar of this. Okay. So what I know based on the equation is I need 3 of these for every 1 of these. So what we can do is figure out how many moles we have to start of each, and then see which one appears to be in excess. Alright, so I'm going to start with the 70.5 milligrams of potassium phosphate. And what I know is there's 1,000 milligrams in 1 gram. And what I know, the molar mass of potassium phosphate is 212.3 grams is 1 mole. And this is going to give me 3.32 times 10 to the -4 moles of potassium phosphate. Okay. And I have 15.0 milliliters of silver nitrate, and that is 0.050 moles in 1,000 milliliters of that, and that will give me 7.5 times 10 to the -4th moles of silver nitrate. Okay, so let's just take a look at what we end up with. So if I have 3.32, the exponent's the same on both, so let's just use the coefficient of it. If I have 3.32 of this, and I need 3 times as much silver, I'm going to need 9 something, more than 9, right? I don't have more than 9. Or I can look at it this way and say if I have 7.5 of this, I'm going to need 2.5 of this. So what I am limited by is my silver nitrate. I don't have enough of that to match what I have in potassium phosphate. Okay, so my answer to the limiting reactant is potassium phosphate. Okay, and then, whoops, not potassium phosphate, it's going to be the silver nitrate, silly me. It's going to be silver nitrate. Alright, and then calculate theoretical yield in grams of the precipitate that forms. So the precipitate is silver phosphate. So I already know how much silver nitrate, how many moles of silver nitrate I have, right? So if I have 7.5 times 10 to the minus 4 moles of silver nitrate, what I know is for every 3 moles of that, based on the balance equation, I get 1 mole of silver phosphate, right? So for 3 moles of silver nitrate, I get 1 mole of silver phosphate, and that 1 mole of silver phosphate is, this is 3, 1 mole of silver phosphate is 418.7 grams. And if I multiply this out, I'm going to come out with let me see, I'm going to want 3 sig bigs, 0.100 grams of silver phosphate. Okay. Alright, so let's take a look at these real quick and then we'll be done with the review. In a can of soda, the major gaseous solute is, well, it's going to be the stuff that's actually dissolved, and the stuff that's dissolved here is going to be carbon dioxide. Alright, what do you think? Which common beverage conducts electricity? Well, it's going to have electrolytes, and which one of these is advertised as having electrolytes? Okay, so Evian water has carbon dioxide in it. I think it's bubbly, right? Milk doesn't have anything that would suggest it's going to conduct. Apple juice has sugars, right? And those sugars are not going to be ionic. They're not going to conduct. So the obvious answer here is going to be Gatorade. When iron 2 nitrate dissolves in water, what particles are present in solution? Well, I'm going to have Fe2 plus, right, and 2 nitrates. So it's going to be B. Lead nitrate and potassium iodide make lead iodide and potassium nitrate. What is the observable evidence that the reaction occurs? Alright, so I got to make something that I can see. I'm not making a gas, so there's no bubbles. And so this is insoluble, so this is going to be a precipitate. So a solid form should be the answer. Okay. When an acid and a base reacts to form a salt and water, the reaction is called a neutralization. It's the definition. When an atom undergoes reduction, it right? Gains electrons. So it should be A. How many milliliters of 0.6 molar sodium chloride are needed to make 250 milliliters of a 0.5 molar solution? So let's do a quick dilution. Okay, so I have, okay, I'm going to do M1V1 equals M2V2. This is the dilution problem. So I have my molarity of my concentrated solution is 6.0 molar. My volume of that I'm trying to figure out, right? And I'm trying to make 0.5 molar, and I'm trying to make 250 milliliters. So I'm going to divide both sides by 6, and when I do that, I should get 20.8. Okay, so it should be 20.8 milliliters. If we have equal concentrations of the following aqueous solutions, so let's say they're all 1 molar, which will have the highest conductivity? So let's assume that they're 1 molar. I like this problem. Okay, so if I have 1 molar of this, I'm going to have 1 molar of this and 2 molar of this for a total of 3 moles of ions, right? I'll have 1 molar of this, 1 of this for a total of 2 moles of ions. 2 moles, 1 mole is 3. 1 mole and 3 moles is going to be 4. 1 mole and 1 mole is going to be 2. So the answer should be aluminum nitrate. Okay. What are the spectator ions in this equation? Okay. So let's just see. This is going to break apart into K plus, OH minus, H plus, F minus, K plus, F minus, plus H2O. Okay? So my common ones are going to be my F and my K. I'm going to be left with OH and H plus. So those will not be spectators. The spectators will be the K and the F. Whoops, what did I do? Oh, good catch. I would have had that one wrong. HF is not a strong acid, it's a weak acid. So this is how we learn, right? Make a mistake. It's weak, so I should not have dissociated that. So it's just K plus. Alright. Which of the following reactions has the net ionic equation H plus plus OH gives me water? Alright, so if you remember, you get this whenever you have what? Strong acid, strong base. So strong acid, strong base, so it should be that one. Weak acid, strong acid, strong base, so it should be the first and the fourth. Let's see if I'm right. Alright. Which has the highest concentration of sodium ions? Okay, so if I have 0.35 molar of this, I've got 0.70 molar of sodium, right? I'll just say 0.4. I've got 3 of them, so that's going to be 1.2 molar. 0.5. This is just going to be plain old 0.8. This is going to be plain old 1.0. So the winner should be sodium phosphate. Alright. And that's it.